Alright, easy problems are done. Now we're actually going to kick off the training wheels and we're going to do some actual real problems. And so far, in this class we've just worked with all kinds of different methods of analysis, and I like this problem. This one's not in the book. I made this one up, and it just, we start to basically build off everything that we did in chapter 2 and chapter 4 and in chapter 7, and how we're actually going to put all those concepts together now. So with this one, we started off with basically a circuit in which we're looking for the total response for the current through the inductor, and remember tau for the inductor is L over R. But here we got 5 amp source on the left and also a 100 volt source on the right. Switch opens at t equals 0, so the original current for t less than 0, that initial current flowing through that inductor, is going to be dependent upon that 5 amp source and then the 100 volt source. But instead of utilizing chapter 3 methods like KCL or anything like that, we can just go ahead, do a source transformation, take the 100 volt source, turn it into a 10 amp source by dividing 100 volts with 10 ohms. Sure enough, we take 10 amps, put that in parallel with 10 ohms, all elements are in parallel. Thing is though, we want that current through the inductor, and that inductor was in series with that 15 ohm resistor. So all we have to do, guys, is go ahead, see all elements are in parallel, we just need to combine our two sources together and then perform current division with basically the 10 ohm, 35 and 25 ohm resistors equated in parallel together. And that came out to be equal to 5.93 ohms. Break down the circuit into basically two elements so we can perform current division. Sure enough, 10 amps plus 5 amps gives us 15. 15 times 5.93 over 5.93 plus 15. Bam, right there. Initial current through that inductor, which was the same as the current through that 15 ohm resistor, comes out to be 5.23 amps. From there, t equals infinity, that switch had opened, and basically we cut off the left side of the circuit. So the only thing that we're going to have as far as separate excitation within that circuit is going to be that 5 amp source. So basically the only thing that we have left is 25 ohm resistor and the 15 ohm resistor. Once again, just do current division. So I infinity is equal to 5 amps times 25 over 25 plus 15, rendering a final value of 3.13 amps as the final condition, the final current that's actually going to be flowing through that inductor in steady state. Cool thing is that we see that it actually dies down 4.23 amps all the way down to 3.13 amps, which is our steady state. Now as far as tau, the time constant, tau is equal to L over R Thevenin. But when we turn off that current source, remember that is an open circuit. And so sure enough, here we have 25 ohms and then the 15 ohm resistor, but these two are actually in series due to the relationship of the inductor looking into the circuit. Sure enough, 15 and 25, when we combine these two together, that node collapses, and what we're left with that equivalence are the two nodes that are in parallel with basically that inductor. So sure enough, 2 over basically 40 gives us 0.05 seconds. We go through and we formulate our total response based off the same form as we would for the voltage across the capacitor. Remember that the inductor's time constant is different. So sure enough, go through and we formulate 3.13 plus 1.1 times e to the negative t divided by 0.05 amps. Don't forget here too that throughout this whole entire process, the inductor is acting like a short, because once in steady state, that change in the current goes away, which means that that magnetic field has become stabilized. Then basically the voltage goes to 0, and that's why we model that as a short. No change in current, voltage is 0, therefore we have a short. Alright, more problems coming up.